Programming languages are what programmers use to express themselves so that the computer can understand them. Today, we get into the details. Welcome to Kopek Explains Software, the podcast where we make computing intelligible.
All right, Dave. Today our topic is, what is a programming language?
Well, should we start? That's such a big topic. There's so many different programming languages. How do we go about this?
I think we just start with the definition and then we'll think about the ways that programming languages are organized and see where the conversation takes us.
Well, a programming language is a medium for a programmer to express themselves to the computer. The computer at its base only speaks machine code. Those are the very simple instructions like add two numbers together, load this variable from memory, put this thing into memory that the microprocessor understands. But programming in machine code is quite difficult. So programming languages are higher level abstractions that are on more of a human level to make it easier for us to express our ideas so that the computer can understand them.
So this is how a programmer is going to get the computer to do whatever it is that they want it to do.
Exactly. So when you hear the terms coding, programming, software development, software engineering, all of those activities are basically programming, using programming languages to instruct the computer to do some task.
And there are some different types of programming languages.
So one way we can categorize programming languages is by what level they're at away from the machine code. So if we think about the machine code as the lowest possible level, then we might say one level higher would be what's called assembly code. Now, machine code is going to be specific to each different microprocessor architecture. So there's one type of machine code for Intel x86 microprocessors, and there's a different type of machine code for ARM microprocessors. Assembly language is basically just a human-readable form of the machine code. It's one level higher, a little bit more abstracted. Instead of just using hexadecimal and binary to represent each of the instructions, we use more English-like words, like we might actually see the word add, or we might actually see the word load to indicate each of those individual instructions. But it's still very, very small, very piecemeal instructions that indicate just one little activity, one little step that we want to do. It's nice to be able to work at an even higher level, at an even more abstracted level that's even more human-like. So while machine code goes all the way back to the first computers in the 1940s, in the 1950s, they started inventing what we call higher level languages. The first two higher level languages that we still use today that came out of the 1950s are Fortran and Lisp, which some of our listeners might have heard about. Now, there's a lot of higher level languages, and they get even more and more abstracted and further away from machine code over time as more and more programming language theory has developed. So we'll talk about different paradigms later on for these higher level languages. But what you need to know about them in general is that they have constructs that allow multiple of these simple machine instructions to be figured out at once. So for example, let's say I want to do some kind of formula. Right? Let's say I want to do some mathematical formula. Instead of going down and describing every single step that the computer would need to do the formula, in some higher level languages, I can just write out the formula. And the programming language, using its compiler or interpreter, which we'll talk about later on, can figure out what those very small, low-level, machine-level instructions need to be to do the formula. But me as the programmer, I might just write out the formula.
So these higher level languages almost condense assembly languages or make it easier for a programmer to get their idea from their brain to the computer.
Right, in these higher level languages, we have to write less and we think more in human level constructs instead of thinking at the machine's base level. So it allows us to write less but still do the same thing that we could have done by writing a lot more using machine code. Now, of course, I'm simplifying things a lot today. I'm trying not to use too much theory today and just try to put things as simply as possible.
So another way to think about a programming language is the paradigm that the language operates in. Can you talk about those different paradigms?
So there's 4 major paradigms of higher level programming languages. There are procedural languages, there are object-oriented languages, there are functional language, and there are logic-based languages. Let me tell you just a little bit about each of those paradigms. So in procedural languages, we group several instructions or statements together into what we call procedures. Sometimes you'll see them referred to as functions. Sometimes you'll see them referred to as subroutines. They all basically mean the same thing. The idea is that we have some area of the code that we can quote unquote call when we want it to execute a certain set of instructions. And then those certain set of instructions will execute, and then we'll go back to where those instructions were called from. The great thing about this is instead of repeating ourselves over and over again, writing the same instructions over and over again, we can just abstract them away into the subroutine, and then we can just call the subroutine each time we need it. So it's a way of organizing code. We organize all the code into these different subroutines, and then we have the subroutines call one another, which allows us to write less code and also be able to think about the code in a more organized way by just being able to think about each individual subroutine. That allows us to do things like test each of the subroutines individually, or just make sure that each of the subroutines is correct individually, instead of having to think about the whole thing as a big mess of spaghetti with tons and tons of instructions. So procedural programming is one of the most basic higher level programming genres. Then what came out now procedural programming goes all the way back to the 1950s. What came out next was object-oriented programming, invented in the late 1960s, early 70s. And that's actually the paradigm that most programming is done in today. Most enterprise programming, at least, is done in object-oriented form today. And in object-oriented programming, we try to abstract away each of the elements of our program into things that are almost analogous to real-world constructs. Let me give you an example. If I was writing a program about animals, I might have one object that represents a dog, and that object might have certain properties and certain actions that it can take. For example, it might have properties like the dog's color. It might have properties like the dog's age. It might have properties like the dog's name. It might have actions it can take like bark or eat or go to the bathroom or go for a walk. So by thinking about the dog as an object, I can encapsulate all these different properties and actions together in one place. So remember, the procedure before that we talked about allowed me to take a bunch of statements and put them together in one place. Now I'm taking both properties and procedures, you can think about those as the actions, and putting them together in one place. Then if I have other items that the dog can interact with, maybe the dog can interact with a human being. That human being might have some properties like a name, like an age, like a profession, maybe a husband or a wife, etc., etc. Interactions, it can even have properties that refer to other objects, and then it can have a bunch of actions that it can take. You can see how this is a really nice way to think as a human being. Object-oriented programming allows us to construct our programs in a way that really makes sense to us from our real-world experience. So then there's another form of programming called functional programming. In this paradigm, we think about trying to construct procedures again, like in procedural programming, but we try to make those procedures more mathematically pure. So we try to make sure that each of those procedures doesn't have what we call side effects, which is interactions with external things outside of the procedure. And we call all those procedures functions in functional programming. The idea of making these functions more pure is that it makes them more provably correct. So they are more similar to a function from mathematics, where we know that whatever its result will be, its output, its return value, will be completely dependent on what goes into the function and on nothing else. By breaking down our program into just these pure functions as much as possible, we can be more sure that it's actually working as we intend it to. There's a lot more to functional programming, but that's probably the most important aspect. And then the last paradigm, which is probably the least used paradigm, is logic programming. And there's really just one programming language that's big in logic programming called Prolog, although other ones exist. And this is, if I can take a bunch of logical propositions, can I go and then find an answer to a problem by combining those propositions together and assert and letting actually the programming language runtime do a lot of the work of resolving them to find some kind of solution. Now, that's a really useful set of ways to think for things like AI programming or sometimes for some business logic, but you don't probably want to write a mobile app or a web app in a logic programming language. It's really not what it was designed for. So that tends to be kind of a niche paradigm. The most common two paradigms are procedural programming and object-oriented programming. That covers the majority of popular languages. But functional programming, which is originally more in the sphere of academia, is becoming more and more popular and is starting to really influence a lot of modern languages. Most of the modern languages of the last 10 years are a combination of ideas from object-oriented programming, also with some ideas from functional programming combined together.
Can you give some examples of which programming languages are which type?
Yeah, absolutely. So let's get logic out of the way. I mentioned Prolog. That's really the only common logic programming language. There's thousands, even tens of thousands of different programming languages in the other paradigms, but I'll give you some of the really popular ones in each. So procedural programming, older languages like C, Pascal, BASIC are probably the most common procedural programming languages that are still in use. Object-oriented programming languages are languages like Java, JavaScript, although it also has some functional influences. C++ can be programmed in multiple different paradigms, but its big thing that it added to C was that it became object-oriented on top of just being able to be programmed in a procedural way. There's a lot of them. I mean, if you take almost any language of the last 20 years, it's probably an object-oriented language. Python is an object-oriented language. Functional programming, there are some pure functional languages like Haskell and Scheme, but there are also a lot of modern languages that have influences from functional programming but are also object-oriented. So a couple modern languages that people might have heard of are Apple's Swift, which definitely can be programmed in a object-oriented way, but it can also be programmed in a functional way if you would like. Other modern programming languages like Dart and Kotlin are probably mainly object-oriented languages, but they also have functional influences on them as well. The purely functional languages like Haskell and Scheme tend to be more popular in academia than they are in the real world, but again, there is definitely some influence from functional programming in modern languages like Swift and Dart.
So when a programmer is getting ready to work on a project or create something, how are they going to choose which language to use?
So we would like to think that people are always choosing the best language, but in reality, a lot of this is fads and popularity, but for good reason, and here's the good reason. When you work on a project, you're going to usually need to work with other people. And just like it's important when we work with other people that we speak the same human languages, it's also important when we work with other people that we speak the same programming languages. That way we can read each other's code, that way we can improve on each other's work. Also, the bigger the community, the more people that you can potentially get help from. So that means there's going to be more documentation, more people to talk to when you have a problem. But it also means there's going to be more people to hire at your company for that programming language if it has a larger programming language community. Another thing to think about is third-party libraries. The more popular the programming language, the more third-party libraries that you can just use off the shelf that'll help you build the first elements of your program before you get to the parts that you have to write yourself. So it's like you're starting on the 5th floor of building a 10-story building instead of starting from the ground floor, which is really nice. So yes, popularity does play a big role in the programming languages that people pick. You can have the most amazing programming language in the world, but if nobody's using it, it's not going to be that useful because you don't have those third-party libraries, you don't have other people to work with, and you might not have a lot of good tools and other things that help you in development. So yes, unfortunately, popularity and fashion does play a big role in it. But then on top of it, you're going to choose a language that usually is geared for a certain niche. Let me give you some examples. So if you're writing a web app and you're writing the client side of the web app, the part that actually runs in the web browser, well, all web browsers have JavaScript interpreters in them. Sometimes they're JavaScript just-in-time compilers, and we'll talk more about that in a minute. But anyway, they all speak JavaScript. And so you're probably going to write part of your web app in JavaScript. If you're writing a mobile app and you're writing it for iOS, you're probably going to write it in Swift because Swift is Apple's preferred language for writing on its platforms. If you're writing an app for Windows, and it's going to be a Windows desktop app, the main programming languages that Microsoft supports are C# and C++. So it means you're probably going to use one of those languages when you write your Windows desktop app. So there's languages that have kind of been optimized and just preferred by certain vendors for certain niches. And it really means that when you go into that community, into that ecosystem, you're going to end up using that programming language. For example, one more I'll give is Python. So Python has become really popular in the scientific computing community, also in the machine learning community. So two of the most popular machine learning libraries right now are TensorFlow and PyTorch. So if you're going to go and do machine learning, you're going to go program some neural networks, you're probably going to want to use the most popular libraries. Therefore, you're going to end up working in Python. So yeah, it ends up that each of these languages kind of carves a niche for itself. And you also need to think about popularity, and we don't always get to just pick what we think is the best programming language. We often have to think about these other factors as well.
A little bit about what you're talking about is the syntax and semantics of a programming language in some ways.
So syntax and semantics, maybe we should have talked about at the beginning of the episode, but it's really the two different ways that we think about how a programming language is structured. So syntax is kind of like what it looks like. So when I see the actual code in a text file, what does that look like to me? And it is only really skin deep, because when we get to semantics, then we're actually talking about how the programming language works. So what do the different constructs that I can write in that syntax actually do? So syntax is in many ways you might think less important than semantics, because what something looks like and how we actually write it out might sound to you less important than how it works. But actually it can have a big influence on a programming language. For example, C is one of the most popular programming languages in the world. It came out all the way back in the early 1970s. It is still used for so many different kinds of programming, including a lot of low-level programming, that it's been very influential on a lot of other languages. So it's very common for modern languages to have C-like syntax. I'll give you an example. C++, JavaScript, Java, Swift, all to a certain extent have C-like syntax. One of the reasons for that is that it makes people feel comfortable. If they already know another language that has C-like syntax, then when they use one of these other languages that has C-like syntax, they right away feel a little bit more familiar, and it's easier maybe for them to pick up the language. So even though syntax might right away you might think of it off the bat as not as important as semantics, it really does have a big influence on whether a language gets adopted. I'll give you one really specific example of when syntax had a negative influence. So Objective-C was the main programming language for the Mac and for iOS until Swift came out in 2014. And just because it had very different syntax from a lot of other popular programming languages of today, like Java or C++, it threw a lot of people off. And there were actually people who didn't want to learn to program for iOS and the Mac. You'd hear about them all the time because they didn't want to learn the Objective-C syntax, or the Objective-C syntax looked so foreign to them that they couldn't get past it. So yeah, unfortunately, the way that a programming language looks does have a real impact on whether or not people like using it. Another good example is Python. Python has really English-like syntax in some ways. A lot of people say that, or it looks a lot like pseudocode. So pseudocode is like code written in a book that you couldn't actually run and compile, but you could read as code. And because Python looks so similar to that pseudocode that we're used to from books, it makes people feel like it's very approachable to write. And that's a really nice quality of it.
So another way to think about a programming language are the characteristics of it.
Yeah, so there's a lot of other characteristics we could talk about. One of them is whether a programming language is dynamically or statically typed. Now, what's a type? A type is kind of what kind of thing is this part of the program supposed to be? So it might be a variable that we say this variable is supposed to be an integer. This variable is supposed to be a string. A string is like a sequence of text. Or this variable is supposed to be a floating point number. And we also have types for functions. So we might have this function is supposed to return an integer or return a string, etc. So types are really important in programming languages because they help us check that our program is correct. Now, there's two different main paradigms of typing. One is called statically typed. That's where we know the type of all these variables, these functions, before the program is compiled. And we'll talk about what compilation is in a minute, but basically it's when we convert the program from the original programming language to machine code. So it's really nice if we can check all those types ahead of time and make sure that everything is correct. So that's what we can do with a statically typed programming language. But it allows us less flexibility. In a dynamically typed programming language, we're a little more wishy-washy about what the types are before we go to compilation or interpretation. And it allows us more flexibility. We can kind of move things around as the program is running. We can kind of check some of our assumptions, and maybe they don't need to be exactly what we assumed as the program is running, and it gives us a little bit more flexibility. So it's a trade-off. With a statically typed programming language, we are able to check for more correctness before we even compile the programming language. But with a dynamically typed programming language, we get more flexibility.
Another characteristic is going to be the way a programming language does memory management on the computer.
Absolutely.
Can you talk about that?
Yeah, so memory management, there's really three different main paradigms. One is the most basic is manual memory management. This means every time that a part of your program wants to use a certain region of memory, you have to remember that and remember to free it later on so that other programs or your program can use that region of memory. So every time you allocate some memory, you as the programmer have to remember later on I need to go free that memory for other people's use or my own use. That's the most difficult for the programmer because they really need to do a lot of bookkeeping on their own and keep track of what they need to free later on so that they don't forget. You can actually have all kinds of errors that come as a result of that. For example, if you forget to free some memory, your program can leak memory. It could just keep using up more and more memory, and eventually the computer could run out of memory. Another problem you could have when you do manual memory management is you could accidentally use some memory that you had previously freed. You could try to use something that you had already deallocated, and that can cause you all kinds of problems as well. So that's the most tiresome and troublesome for the programmer. It causes all kinds of errors, and it takes a lot of cognitive overhead to think about. A little bit less troublesome is a paradigm called reference counting, and this is usually used with object-oriented programming languages. The idea here is that we're going to keep track of each item's number of uses in the program, and we'll have what's called a reference count for each item. So back to my example earlier about the dog. Maybe I have the dog in my program, and one part of my program, the user is walking the dog, so the dog exists there, so I increase the reference count. Then somewhere else in my program, maybe the dog house has reference to the dog. So I increase the count there. So there's two parts of my program that are keeping track of the dog. So the reference count on the dog is 2. If later on in my program I go to somebody else's house, I never want to worry about that first person's house again, then I no longer need to worry about that user keeping track of the dog, so I eliminate that person, and that decreases the reference count to 1. And I don't need the doghouse anymore, so I eliminate that part of the program, and that decreases the reference count to 0. And then the programming language runtime, whenever it sees the reference count of something go to 0, will automatically free it for me. So I just need to keep track of where am I keeping track of these objects, and then the programming language runtime will automatically free them when there's no longer anything keeping track of them. So it helps me a little bit. It does some of the bookkeeping for me in reference counting. It's not quite as cumbersome as manual memory management. Then the ultimate in terms of programmer productivity, but it does have a little cost, is garbage collection. In garbage collection, I don't need to think about freeing memory at all as the programmer. We let the programming language runtime just think about, is this memory being used anymore? Oh, if it's not, it's going to automatically free it. To do that, it needs to occasionally go scan through everything in memory and see if anything else is using it. And we call that a garbage collector pause when the program takes a little bit of time to go do that. And that can decrease performance, and that gives you less fine-grained control as a programmer. So it's a trade-off. It does cost something. We've gotten really good in the last decade of making it cost very little, but it still does cost something, but it's the least burden on the programmer. So you go from manual memory management, where you have the least amount of performance cost, but you have the most cost on the cognitive overhead of the programmer, to garbage collection, where you have very little cognitive overhead for the programmer, but you have a little bit of performance cost.
So there's a trade-off for each one of these.
Absolutely.
So the last thing, or main topic that I want to ask about, is just how do these programming languages, the different ways that they translate into machine code?
Yeah, so there's 3 different ways and 2 main ones. Let me talk about the 2 main ones first. So there's compilers and there's interpreters. What a compiler does is it tries to take the entire source code of the programming language, and I'm going to specifically talk about ahead of time compilers, and convert it into machine code before the program runs. So what a compiler does is it takes this high-level code that we've written in a text file, something like C, for example, and it takes that C source code and it converts it into machine code before the program runs. And then when we actually run the program, we're just, of course, running the machine code. What an interpreter does is instead of taking the whole thing, it actually, at runtime, takes each statement in the programming language and converts it into machine code on the fly. So it's going one step at a time. Now, there are some benefits to that. The programming language can be a little bit more dynamic. It can be a little bit more flexible when it's built with an interpreter. But by and large, interpreters tend to be a lot slower than compilers. There, of course, are exceptions to every rule, but really the vast majority of interpreted programming languages are going to be slower than any kind of compiled language. Then there is another form. There's something in between. There's what's called a just-in-time compiler. What a just-in-time compiler does is it's kind of a hybrid between an interpreter and an ahead-of-time compiler. It'll go and it'll start interpreting the program, and as it sees chunks of it that are being used a lot, it'll go and compile them on the fly into machine code so that the next time they're used, it calls the machine code. By analyzing the program before it compiles it, it can actually do some optimizations. It can go and say, well, you know what, the way that this part of the program is actually being used, I might want to convert it into slightly different machine code. So there can be some advantages to a just-in-time compiler. There can be some situations where its optimizations will even exceed an ahead-of-time compiler. But as a general rule, it kind of falls somewhere in between an ahead-of-time compiler and an interpreter. So in general, an ahead-of-time compiled language is going to be more performant than a just-in-time compiled language, which is going to be more performant than an interpreted language. But that's a really rough rule. There will be, of course, interpreted languages that are fairly fast, and there will occasionally be just-in-time compiled languages that might be faster than some ahead-of-time compiled languages. So it's not a hard and fast rule, but it gives you a general sense. Now, there can be real differences in performance between programming languages. It's a question I get a lot because I've written books in a few different programming languages. People ask me, well, how performant is this programming language versus this other programming language? And you know what? It can actually be significant if you're working on production level code. So for example, naively written code in Python can be as much as 50 times slower than code written in C. Now, the reality is that if you really care a lot about performance, then you probably are thinking about it from a different perspective than somebody who's just learning programming. And a lot of the questions I get about performance are from people who are learning programming. And if you're just learning programming, you really don't need to worry about it. You know what? The kind of programs you write the first couple years that you're learning programming, you're not really going to run into a lot of performance problems no matter what you're using. So you don't really need to worry about these differences, and it's not really something I would think about when I'm learning programming.
Well, that is a nice transition to my last question, which is what programming language or what advice would you give to someone who's starting out with programming when they're selecting which language to learn?
So my number one piece of advice is whatever language you choose, to stick with it for a while. One of the biggest things I see in people learning programming is this anxiety of, am I learning the right language? And then they kind of switch around a little bit as they're learning. And I think that's a pretty bad idea, actually. I think it's important to get comfortable with one language. What do I mean by comfortable? I mean, I guess if you're in college, a couple semesters in that language, if you're learning on your own, maybe a year learning in that language and getting pretty good at it and getting some payoff where you're able to actually do things that you're interested in that language before you move on to another language. So my number one piece of advice is to stick with one language for a while and get to a point where you feel like you can write something that you're proud of. Then, my next piece of advice is actually to choose a language that has a welcoming and approachable community. So a language that is actually going to give you the resources you need to learn in the way that you want to learn. So if you choose a language that's really obscure, there might not be a lot of, let's say, books about the language, and some people learn well from books. Or there might not be video series about the language, and some people learn well from videos. So I would choose a language that's popular enough, that has a welcoming community. And then the last thing I would think about is, what is your ultimate goal? So I would choose a language that is popular in the niche that you want to eventually develop for. so that you will get that spark that you get from being able to create something you actually wanted to create when you started. Let me give you an example. If you really want to build mobile apps, then I would think starting with learning a language like Swift or Kotlin would be great, so that by the time you get to that 1 year point or that couple of semesters, you can actually program mobile apps. And then you're really going to feel like you got some kind of reward for doing all of this learning, and that will keep you motivated to keep learning. So again, the things I would think about are, what's the community like? Is it a popular enough language that there's going to be resources for me? Is it a language that's in a niche that I eventually want to develop in? And most importantly, stick with the language that you started with for a little while so that you get competence in it before you move on to the next one.
Great. Anything else that our listeners should know about programming languages?
Well, there's so many different programming languages, and I think we've covered a pretty good overview today, but maybe in future episodes we'll get into some specific ones and how they differ from one another and how they're used.
Sounds good.
Well, thanks so much for listening. We really appreciate having you with us. Don't forget to like us on your podcast player of choice, whether that be Overcast or Spotify or Google Podcasts or Apple Podcasts. Leave us a rating or a review. It really helps with the popularity of the show. And we have a Twitter account. What's our Twitter account?
At Kopec Explains. That's KOPECEXPLAINS.
Yeah, please follow us and send us your feedback and tell us what you think might be a good future topic. Well, thanks so much for listening, and we'll see you next week.
Bye.